Welcome to the video on the normal curve. Let me get the title up on the board for us. Normal curve. Probably not a new concept to most of you, but nevertheless, let's just kind of jump into it. So the normal curve is one of the most fundamental distributions in all of statistics, and really we should probably start there. Is what is the normal curve? Well, the normal curve is really otherwise known as, or also known as, normal distribution. And building off of our other, put this all in quotes here, building off of our other videos on frequency, really the y-axis here, and I apologize for such a crude drawing here, but it's really not normal or symmetrically shaped here, but it's the best I can do freehand. For this particular curve, we've got a y-axis and we've got an x-axis. And on the y-axis is just going to be frequency, just like the rest of our frequency distributions that we have done. The normal curve is just simply that. It's a normal distribution looking at frequency of some variable x down here. Some x variable could be anything. It could be a dichotomous, heads, tails, males, females. It could be continuous, looking at the number of push-ups or pull-ups, exam scores. So down here could be discrete or continuous in terms of the types of variables that we have. Okay, so basically what we know then is that, or what we have discovered over time, is that observations on any kind of variable x will kind of approximate this normal distribution, or what we call this normal curve, oftentimes referred to as kind of like a bell-shaped curve. Really, this was discovered by a German mathematician, which was Carl Friedrich Gauss. So the normal distribution is, again, also known as the Gaussian distribution. What we need to know then about this distribution is, what is it going to kind of represent here? So the peak of this is representing the most frequency, right? So if you were to kind of take the peak and go over and extend a line from the peak over to the y-axis, that would represent the highest frequency observations on your variable x. And so what we want to do is look at what are these. You can break this into sections. And so I'll do my best here to kind of draw these on here. But when you kind of look at these, the way this kind of breaks down, let me try to go right down the middle here. So if you look at something, we'll call this the middle right there, then you would have essentially 50% of the distributions on the left side of this point and 50% of the observations on the right side of it. And so as we kind of look at this on a standard normal curve, and a standard normal curve, let me put this up here, standard normal uses standardized scores. That's going to be another video to look at how you actually standardize a score. But for right now, we just want to get the mechanics of what the actual distribution looks like. Okay, so going down the middle here, with a standardized score, this middle value would give us a standardized score of 0. I'm just going to try to put that down there as a big 0. And then what we're going to do is build a few other pieces in here. So let's call this one right here positive 1 sigma. Use the lowercase Greek letter sigma here. Then we'll use go positive 2 sigma, and then try to equally space this and go positive 3 sigma. We'll explain what these sigma mean here in just a minute. And then if we go over here, we'll go negative 1 sigma, negative 2 sigma, negative 3 sigma. Okay, so let's look at, we're just going to kind of extend these up. We're just going to, kind of build the best we can in here. Okay. So I'm just going to kind of do my best here to build some separation lines in. Give me just a second to build these in. Okay, so between 0, a standardized score of 0, and plus 1 sigma, you will catch essentially 34.13% of the scores. Likewise, just on the left, between 0 and negative 1 sigma, you'll capture 34.13% of the scores. Between plus 1 sigma and plus 2 sigma, you'll capture 13.59% of the scores. And again, 13.59%. And why are all the numbers equal on the right and the left? Because the curve is supposed to be symmetrical. Now, because I can't draw a perfectly symmetrical curve, it's not going to look that way, but just rest assured that it is. And so between 2 and 3 sigma, this would be 2.14%, 2.14%, and then essentially after you get way out here, after 3 sigma, going out to even say 4 sigma, and we could even put 4 sigma out here. For sigma, it'd be 0.13%, and we could build 4 sigma in over here. Negative 4 sigma would be 0.13%. Okay, so looking at this, what is this going to kind of, what kind of story is it going to help tell us here? So I'm just going to scroll down just a hair here for us, and I'm going to try to build in another piece. And so essentially then, if you look at between, and you add these up, between plus 1 and minus 1 sigma, you're getting approximately 68%, or really 68.26% of the scores are between plus 1 and negative 1 sigma. Sigma also means standard deviation. I'll clarify that in just a minute here. Building it out from here, if you go from negative 2 to positive 2, you're going to capture 95.44% of the scores, or the observations. And again, if you just kind of going with this concept, we keep building it out from plus or minus 3 sigma, 99.72%. And just to take it one more, let's go to 4 sigma. This will give us 99.98% of the scores if you go all the way out to 4 sigma. Okay, so let me just scroll this back up for us. let's just build in the other piece here, that is what are these sigmas. So if you go back a few videos in this particular class, we talked about the difference between statistics and parameters. Parameters are things that describe the population. So the mean of the population is signified by mu. The variance of the population is sigma squared, and the standard deviation of the population is sigma. So what these sigmas mean down here, these are the standard deviations of the actual population. Well, we don't always have these population parameters. We don't know what the mean of the population of interest is, and we don't know what the variance and standard deviation are. So what we do is we calculate estimates of those parameters, which are known as statistics, and the statistical equivalence of these, whereas mu is going to be our x bar, our mean, our variance becomes s squared. So we're using the sample and calculating this statistic called s squared to estimate sigma squared. And then we're going to have s, which is our standard deviation. And so in the following videos, what we will do is look at how we actually take sample data, because this might seem abstract to you right now, take sample data and from our mean standardize the score using the standard deviation, and then plot those scores on a frequency distribution like this and see what we get. So that is it for an introductory video on the normal curve and the percentages.